Hello friends, welcome back to my channel. Today we are going to solve 41th question from GATE 2022. This is a metric space question. We are given set of rational numbers with D as a metric space where D of xy is equal to modulus of x minus 5. So this is the usual metric, standard metric. And E is the set of all rational numbers whose square lies between 2 and 3. And we have to find out if E is closed and if E is compact. So first let us write E explicitly. So 2 strictly less than p squared less than 3, this implies minus root 3 less than p less than minus root 2 or root 2 less than p less than root 3. So this says E is equal to set of and p belongs to q. So E is set of all rationals in minus root 3 minus root 2 union with root 3 root 2 root 2 root 3, right? So is set of all rationals in this union of intervals. Okay, now we have to find out if E is closed. So for that we have one theorem in metric space. If A is a subset of Y is a subset of X, where X is a metric space and Y is its subspace, then A is closed in Y if and only if there exists B subset of X such that B is closed in X and A is equal to B intersection Y. So Y A is closed in Y if and only if there is a closed subset of X such that whose intersection with Y is equal to A, right? So if we can write E as some closed set in R intersection with Q, then A is closed in Q, right? So let's check. Now note that this plus or minus root 2 plus or minus root 3, this does not belong to Q, right? So therefore we can write this E as Q intersection closed interval minus 2 minus root 3 minus root 2 union with root 2 root 3. These two sets are equal because these endpoints of the intervals does not belong to Q, right? So these two are equal, so we can write E as this. Now note that this set in the bracket, this is union of two closed intervals in R, so this is closed in R, this is closed in R. Thus we can write E as intersection of something that is closed in R with Q, right? Therefore from this theorem E is closed in Q, right? Okay, now let us check if E is compact. So for that also we have one theorem. Consider the same hypothesis as this theorem. Then we say A is compact in Y if and only if A is compact in X. So using this theorem we can check if A is compact in Q. Now note that E is equal to Q intersection with minus root 3 minus root 2 union with root 2 root 3. Now note that this thing, if we consider E as a subset of R, not as a subset of Q but as a subset of metric space R, then E closure, this is equal to this, right? Therefore E is not compact, E is not closed in R, right? Now it is not closed in R, so it is not compact because every compact subspace of R is closed. So E is not closed in R, so it is not compact in R. Therefore E is, this is closure in R, note that. So E is not compact in R since it is not closed, right? So by this theorem, if E is not compact in R, then E is not compact in Q as well. Therefore E is not compact in Q. This E is closed but E is not compact, so this is the solution. Okay, so that is option A. So option A is correct. A is closed but it's not compact. So I hope you all understood this question. See you in the next video. Thank you.